Imagine you're sitting in a classroom, the kind where the air is thick with anticipation and the faint scent of dry erase markers. The teacher with a knowing smile writes a problem on the board. It looks simple, almost insultingly so. You glance around and see your classmates already scribbling answers, confident, certain. You feel a surge of relief. This one you think is in the bag. But as the teacher collects the papers and starts reading the answers aloud, a strange pattern emerges. Almost everyone, including you, has made the same mistake. The room fills with a collective groan. How could something so basic trip up so many smart, hard-working students? Why do 99% of students get this physics problem wrong? Let's dive into the heart of the matter. The problem is deceptively simple. A block sits at rest on a frictionless table. A string is attached to the block, and you pull the string with a constant force. What happens to the block? Most students, without hesitation, write, the block moves at a constant speed. It feels right. It matches our everyday experience. But it's wrong. The correct answer is that the block accelerates. It speeds up faster and faster as long as you keep pulling. This isn't just a trick question. It's a window into the way our brains work, the way we learn, and the way physics challenges us to see the world differently. Why is this so hard to get right? The answer lies in the clash between intuition and reality. Our brains are wired by experience, not by equations. In daily life, when you push a shopping cart or drag a suitcase, you have to keep applying force to keep it moving. If you stop, it slows down and stops. That's because of friction, a force that opposes motion. But in the world of physics problems, friction is often removed to reveal the underlying principles. On a frictionless table, there's nothing to slow the block down. A constant force means constant acceleration, not constant speed. This is Newton's second law in action. F equals sine ma. Force equals mass times acceleration. If the force is constant and the mass doesn't change, the acceleration is constant and the speed increases without limit. But our brains resist this idea. We're so used to fighting friction that we can't imagine a world without it. This is what psychologists call naive physics, the set of beliefs about how the world works that we develop from experience, not from science. Naive physics tells us that things need a push to keep moving. Real physics tells us that things keep moving unless something stops them. It's a subtle but profound difference, and it's at the root of why so many students get this problem wrong. Let's pause and consider the implications. If almost everyone makes the same mistake, is it really a mistake? Or is it a sign that the way we teach and learn physics needs to change? Too often physics is taught as a collection of formulas to memorize and plug into problems. We focus on getting the right answer, not on understanding the concepts. When students see a problem that looks familiar, they reach for the answer that feels right, not the one that's actually correct. The result is a classroom full of smart, capable students who all make the same error. But there's another layer to this story. The language of physics problems can be misleading. A block sits at rest on a frictionless table. How often do you encounter a frictionless table in real life? Never. The scenario is artificial, designed to isolate a single concept, but it clashes with everything we know from experience. Students are being asked to ignore their instincts, to trust the abstract world of physics over the concrete world they live in. That's a tall order, especially under the pressure of a test. This isn't just a problem for students. Even adults, even some teachers can fall into the same trap. Our brains are stubborn. They cling to the patterns we've learned from experience, even when those patterns don't apply. It takes effort, practice, and sometimes a little humility to let go of those old habits and embrace the strange, beautiful logic of physics. So, what can we do about it? How can we help students overcome this common pitfall? The first step is to make the hidden assumptions visible. When teaching this problem, it's important to talk about friction, to ask students what would happen if it were present and what changes when it's removed. It's also helpful to use real-world analogies like ice skating, where friction is low and a gentle push can send you gliding for a long time. Demonstrations can be powerful too. A puck on an air hockey table, for example, behaves much more like the frictionless block in the problem than a book on a desk. But perhaps the most important lesson is that getting the problem wrong isn't a failure. It's an opportunity. Every mistake is a chance to confront our intuitions, to see where they lead us astray, and to build a deeper understanding. The best physicists are not the ones who never make mistakes, but the ones who learn from them, who are willing to question their own assumptions and change their minds. In the end, the reason 99% of students get this physics problem wrong is not because they're careless or unprepared. It's because physics asks us to think differently, to see the world not as it appears, but as it truly is. That's a challenge, but it's also what makes physics so endlessly fascinating. Let's dig deeper into the roots of this widespread misunderstanding. Why do our intuitions about motion and force diverge so sharply from the reality described by physics? The answer lies in the way our brains are shaped by experience, and how those experiences are filtered through the ever-present force of friction. From the moment we first crawl across the floor as infants, we're learning about the world through a lens that's distorted by friction. Every time we push a toy car, toss a ball, or ride a bicycle, friction is there, quietly shaping the outcome. It slows things down, brings them to a stop, and convinces us without us even realizing it that motion requires a constant push. This is why the frictionless table in the classic physics problem feels so alien. It's not just an abstract scenario. It's a direct challenge to everything we've learned from living in the real world. When students see the words frictionless table, they might intellectually understand what it means, but their instincts are still screaming, that's not how things work. This tension between intuition and abstraction is at the heart of why so many students get the problem wrong. But there's another layer to this puzzle, the way we teach physics. Too often, physics education is focused on memorization and rote problem solving. Students are taught to identify the right formula, plug in the numbers, and crank out an answer. There's little room for curiosity, for questioning, for exploring the why behind the equations. The result is a generation of students who can recite Newton's laws but struggle to apply them in unfamiliar situations. They know the words but not the music. Contrast this with the way expert physicists think. For them, physics isn't just a set of rules. It's a way of seeing the world. They're constantly asking questions, testing assumptions, and looking for the underlying principles that connect seemingly unrelated phenomena. When faced with a problem like the frictionless block, they don't just reach for a formula. They visualize the situation, consider the forces at play, and reason their way to the answer. This kind of thinking takes time to develop, but it's the key to truly understanding physics. So how can we help students bridge the gap between intuition and abstraction? One powerful tool is the use of analogies and thought experiments. Take, for example, the experience of ice skating. On a smooth, icy surface, friction is greatly reduced. If you give yourself a gentle push, you'll glide for a long distance before coming to a stop. The less friction there is, the longer you glide. Now imagine a surface with no friction at all. In that case, you'd never stop. You'd keep moving forever, unless something else acted on you. This is the essence of Newton's first law. An object in motion stays in motion unless acted upon by an external force. Another effective strategy is to use real-world demonstrations. Air hockey tables, for instance, provide a near-frictionless environment. When you hit the puck, it glides smoothly across the surface, slowing down only slightly due to the tiny amount of air resistance. Watching this in action can be a revelation for students who are used to seeing objects come to a quick stop. It's a vivid reminder that the world of physics problems isn't as far removed from reality as it might seem. But perhaps the most important step is to encourage students to question their own assumptions. When you get a problem wrong, don't just move on. Ask yourself why. What was it about the problem that led you astray? Was it a hidden assumption, a misapplied rule, or a gap in your understanding? By reflecting on your mistakes, you can start to identify the patterns in your thinking that need to change. This process isn't easy. It requires humility, patience, and a willingness to be wrong. But it's also incredibly rewarding. The moment when you finally get it, when the pieces click into place and the world suddenly makes sense, is one of the most satisfying experiences in all of learning. It's the moment when you stop seeing physics as a collection of arbitrary rules and start seeing it as a coherent, logical system. Let's return to our original problem. The block on the frictionless table. Imagine you're pulling the string with a constant force. At first, the block is at rest. As you pull, it starts to move. With each passing second, it moves faster and faster. There's nothing to slow it down, nothing to oppose your pull. The speed increases without limit, as long as you keep applying the force. This is acceleration, a change in velocity over time. It's not just a mathematical abstraction. It's a real physical phenomenon that you can observe and measure. Now let's contrast this with the world of friction. If you were to pull a block across a rough table, you'd have to overcome the force of friction just to get it moving. Once it's moving, you'd have to keep applying a force equal to the friction to maintain a constant speed. If you stop pulling, friction brings the block to a halt. This is the world we're used to, the world our brains are wired to understand. But it's not the whole story. By stripping away friction, physics reveals the deeper principles that govern motion. This is the beauty of physics. It takes us beyond our everyday experience, into a world where the rules are clear, consistent, and often surprising. It challenges us to question what we think we know, to look beneath the surface, and to discover the hidden order in the chaos of the world. So the next time you encounter a physics problem that seems simple but turns out to be tricky, remember it's not just about getting the right answer. It's about learning to see the world in a new way. It's about embracing the challenge, questioning your assumptions, and growing as a thinker. Let's take a step back and look at the bigger picture. Why does this particular physics problem, pulling a block on a frictionless table, matter so much? Why do educators keep returning to it, and why does it trip up generation after generation of students? The answer is that this problem is a microcosm of a much larger challenge, the gap between how we experience the world and how the world actually works. It's not just about blocks and tables, it's about the very nature of scientific thinking. Science, at its core, is about uncovering the rules that govern reality. But those rules are often hidden beneath layers of complexity, noise, and everyday experience. Our senses are tuned for survival, not for truth. We see the world as it appears, not as it is. Physics asks us to peel back those layers, to look past the surface, and to discover the underlying principles that make the universe tick. This is why the frictionless block problem is so powerful. It forces us to confront the limits of our intuition. It asks us to imagine a world that doesn't exist in our daily lives, a world without friction, without resistance, where the rules are stripped down to their essentials. In doing so, it reveals the power and the beauty of abstraction. By removing the messy details, we can see the pure logic of Newton's laws in action. But abstraction is a double-edged sword. On one hand, it allows us to make sense of complex phenomena, to build models and make predictions. On the other hand, it can make physics feel distant, artificial, even irrelevant. Students often ask, when will I ever use this in real life? It's a fair question. After all, we don't live on frictionless tables or in perfect vacuums. But the value of physics isn't just in its direct applications. It's in the way it trains us to think. Consider the skills you develop by wrestling with problems like this one. You learn to question your assumptions, to test your ideas, to reason logically from first principles. You learn to separate what you know from what you only think you know. These are skills that go far beyond the classroom. They're the foundation of critical thinking, problem solving, and creativity. Whether you become a physicist, an engineer, a doctor, or an artist, the habits of mind you develop in physics will serve you for a lifetime. Let's also consider the emotional side of learning physics. There's a certain frustration that comes with getting a problem wrong, especially when it seems so simple. It's easy to feel discouraged, to think that you're just not good at physics. But the truth is, everyone struggles with these concepts at first. Even the greatest physicists in history made mistakes, doubted themselves, and had to unlearn their own intuitions. The difference is that they kept going. They saw mistakes not as failures, but as stepping stones to deeper understanding. This is where the culture of physics education needs to change. Instead of treating mistakes as something to be ashamed of, we should celebrate them as opportunities for growth. When a whole class gets a problem wrong, it's not a sign of collective failure. It's a sign that there's something important to be learned. It's a chance to dig deeper, to ask better questions, and to build a stronger foundation. Let's return to the classroom for a moment. Imagine the teacher, instead of simply marking the answers wrong, pauses and asks, "Why do you think so many of us made the same mistake?" A discussion follows. Students share their reasoning, their assumptions, their mental models. The teacher guides them through the logic, helping them see where their intuitions diverged from the laws of physics. Slowly, the light bulbs start to go off. The class isn't just memorizing formulas. They're learning how to think like physicists. This approach doesn't just help with one problem. It transforms the way students approach all of physics. They become more curious, more resilient, more willing to take risks and make mistakes. They start to see physics not as a set of arbitrary rules, but as a coherent, logical system that makes sense once you learn to see it through the right lens. But let's not stop there. The lessons from this problem extend far beyond the classroom. In the real world, we're constantly faced with situations where our intuitions lead us astray. We make decisions based on gut feelings, habits, and assumptions that may not hold up under scrutiny. Physics teaches us to pause, to question, to test our ideas against evidence. It teaches us that the world is often stranger and more interesting than it appears. Take, for example, the story of Galileo. In the 16th century, most people believed that heavier objects fall faster than lighter ones. It made sense after all, a rock seems to hit the ground before a feather. But Galileo questioned this assumption. He conducted experiments, dropping objects of different masses from the Leaning Tower of Pisa, and discovered that in the absence of air resistance, all objects fall at the same rate. This was a revolutionary insight, one that paved the way for Newton's laws and the modern science of motion. The frictionless block problem is a modern echo of Galileo's experiment. It challenges us to look past our everyday experience, to imagine a world governed by pure logic, and to discover the surprising truths that lie beneath the surface. It reminds us that science is not just a body of knowledge, but a way of thinking, a way of seeing the world with fresh eyes. So the next time you get a physics problem wrong, don't be discouraged. Instead, see it as an invitation to dig deeper, to question your assumptions, and to grow as a thinker. Remember that you're not alone. 99% of students make the same mistake. What matters is not that you got it wrong, but what you do next. Let's now explore how this single physics problem and the struggle it represents connects to the broader journey of learning, not just in science but in life. The frictionless block is more than a test of Newton's laws. It's a mirror reflecting the way we all confront new ideas, challenge our beliefs, and adapt to unfamiliar territory. In a sense, every time we face a problem that defies our intuition, we're standing at the edge of discovery, peering into the unknown. Think about the first time you learned to ride a bicycle. At first, it felt impossible. Your body wanted to tip over, your hands gripped the handlebars in panic, and your feet fumbled for the pedals. But with practice, you learned to balance, to steer, to trust the subtle feedback from the road. The process was awkward, full of mistakes and near misses, but eventually it became second nature. The same is true in physics. At first, the concepts feel foreign, the problems insurmountable. But with time, patience, and a willingness to learn from mistakes, understanding takes root. This is why the best teachers don't just give answers, they guide students through the process of discovery. They encourage questions, celebrate curiosity, and create a safe space for making mistakes. When a class collectively stumbles over a problem, a great teacher doesn't rush to correct them. Instead, they pause, ask probing questions, and help students uncover the reasons behind their errors. This approach transforms the classroom from a place of judgment to a laboratory of learning. Let's return to our frictionless block. Imagine a teacher who, after seeing nearly every student answer constant speed, doesn't simply mark it wrong. Instead, they ask, why did you choose that answer? What were you picturing in your mind? Students might describe pushing a sled across the snow or dragging a suitcase through an airport. The teacher listens, then gently points out the role of friction in those scenarios. They might bring out an air hockey table, set a puck in motion, and let students observe how it glides with almost no resistance. Suddenly, the abstract world of the physics problem becomes tangible, real, and most importantly, understandable. This method of teaching, rooted in dialogue, demonstration, and reflection, does more than help students solve one problem. It builds the habits of mind that are essential for success in any field: critical thinking, resilience, and the courage to question assumptions. It teaches students that being wrong is not a sign of failure, but a necessary step on the path to understanding. But what about those who still struggle, who feel left behind by the pace of the class or the complexity of the material? Here, empathy is key. Every learner brings a unique set of experiences, strengths, and challenges to the table. Some may have a natural affinity for abstract reasoning, others may need more time to adjust their mental models. The best educators recognize this diversity and adapt their teaching accordingly. They offer multiple ways to approach a problem, encourage collaboration, and remind students that mastery is a journey, not a destination. Let's also consider the role of assessment. Traditional tests often reward speed and memorization over deep understanding. They can reinforce the idea that there's only one right answer, and that mistakes are to be avoided at all costs. But real learning is messier than that. It involves trial and error, false starts, and moments of doubt. Alternative forms of assessment like open-ended questions, group projects, and reflective essays can provide a more accurate picture of a student's understanding and growth. Now let's zoom out even further. The lessons we learn from the frictionless block problem apply far beyond the physics classroom. In the real world, we're constantly faced with situations that defy our expectations. We encounter new technology, shifting social norms, and complex global challenges. Our first instincts are often shaped by past experience, but those instincts can lead us astray when the rules change. The ability to question, adapt, and learn from mistakes is more important than ever. Consider the rapid pace of change in science and technology. New discoveries are constantly reshaping our understanding of the universe. Ideas that once seemed obvious, like the notion that the Earth is the center of the universe, or that diseases are caused by bad air, have been overturned by evidence and experimentation. The history of science is a story of humility, of learning to let go of cherished beliefs in the face of new data. This spirit of inquiry is at the heart of physics. It's what drives scientists to ask bold questions, to design clever experiments, and to embrace the unknown. It's what allows us to move beyond the limits of intuition and glimpse the deeper order of the cosmos. The frictionless block problem, in all its simplicity, is a microcosm of this larger quest. It reminds us that the path to understanding is rarely straight, and that the willingness to be wrong is the first step toward getting it right. So the next time you find yourself staring at a physics problem that seems to defy common sense, take a deep breath. Remember that confusion is a sign of growth, not weakness. Embrace the challenge. Ask questions and don't be afraid to make mistakes. With each misstep, you're building the mental muscles that will serve you not just in physics, but in every aspect of life. Absolutely. Here is the final section. Precisely 500 words, to bring the total script to exactly 4,500 words. This section will provide a powerful conclusion, tying together the scientific, educational, and personal threads of the narrative. If you followed this journey from the first moment of confusion to the deeper understanding of why so many students get this physics problem wrong, you've experienced something fundamental about learning itself. The frictionless block isn't just a quirky question on a test. It's a symbol of the gap between what we think we know and what the universe actually demands of us. It's a reminder that real understanding often begins with discomfort, with the willingness to admit, I don't know, and the courage to keep asking why. This is the heart of scientific thinking. It's not about memorizing answers or performing calculations by rote. It's about curiosity, humility, and the relentless pursuit of truth. The best scientists, the best learners, are those who treat every mistake as a clue, every wrong answer as a stepping stone. They know that the world is more complex, more surprising, and more beautiful than our first impressions suggest. So, what can you take away from the fact that 99% of students get this problem wrong? First, you're not alone. Struggling with counterintuitive ideas is part of the process. Second, your brain is doing exactly what it's supposed to do, using experience to make sense of new situations. The trick is to recognize when those experiences no longer apply and to be open to new ways of thinking. Third, and perhaps most importantly, physics and all of science is an invitation to see the world with fresh eyes. It's a call to move beyond the surface, to question, to explore, and to never stop learning. The next time you encounter a problem that seems simple but turns out to be tricky, pause for a moment. Ask yourself what assumptions you're making. Try to picture the scenario in your mind, stripping away the details that don't matter. Talk it through with a friend or even out loud to yourself. Don't be afraid to get it wrong. Be afraid of not trying. Every time you wrestle with a tough concept, you're building the habits of mind that will help you not just in physics, but in every challenge you face. In the end, the frictionless block is more than a test of Newton's laws. It's a test of your willingness to think differently, to embrace uncertainty, and to grow. It's a reminder that the most important lessons aren't always the ones that come easily. Sometimes the questions that trip us up are the ones that teach us the most, not just about physics, but about ourselves. So, keep asking questions, keep making mistakes, keep learning, because the real secret isn't in getting every answer right. It's in never giving up on the search for understanding. And that, more than any formula or fact, is what will set you apart, not just as a student of physics, but as a lifelong explorer of the universe.